SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 48. So we were actually talking about arc welding processes and particularly describing the voltage drop across an arc. So we sort of tried to find out what is the relationship between the arc space. For example, this is the cathode space, this is the arc column, this is the anode space, and the respective voltage drops, where we actually reasoned out why it is that the voltage drops are pretty steep in the areas of cathode space and anode space, but when it comes to the arc column, it may not be that steep. And one of the reasons is that basically have shields of opposite ions across the electrodes in question, which has to be penetrated, and so there is an energy loss if the electron comes out of the cathode or goes into the anode because of the surrounding charges. Whereas in the arc column, it is more or less like a resistive component, so there is not much which can be done about this thing actually. We also talked about the various relationships between the voltage and current for arcs, and we figured out that, or we reasoned out that for an arc current of less than 50 amperes, the arc is more or less cylindrical, because of which the surface to volume ratio is basically inverse of the diameter. So with the increase in diameter, there is a surface area reduction and the volume decreases, and because of which there is more less heat transfer, and the arc gets hotter and the conductivity goes up or resistivity goes down. Whereas after 50 amperes, there is a substantial amount of current, over which the voltage does not change much, because obviously the arc starts bulging and there is more resistive path which happens because of this bulge, and so there is a sort of a balance between the heat of the arc and the bulging, because of which the resistance would increase, and so on one hand the conductivity increases, on another hand the path length increases. Beyond a certain time, beyond close to about 200 amperes or so, you will see that now the dominant factor is basically the bulging out arc, and because of which the resistivity would again increase, and there is a VI relationship which is sort of non-linearly increasing. So that is how we reasoned out how this characteristic of voltage versus current comes. So obviously for different arc lengths, we would actually have different voltage current characteristics. In this particular case, for example, these are two different characteristics for arc length L and L plus delta L. So this is an additional delta L of the arc, for which the voltage characteristics you can find out is totally different. So the operating characteristics of the power source, which is feeding the the system, is really dependent on the intersection point of the the VI relationship of the power source with respect to these arc length characteristics, and wherever there are intersection points at the point of operation of the particular arc. So as a first approximation, we can assume that the conductivity of the arc column is kind of independent of the arc length, okay. But as you know that the bulging out phenomena happens a little bit later on, because of which length comes into picture. So we can say that V is equal to some component which is the electrode drop component plus BL, where this is the length based drop in the voltage, or length based increase in the voltage, and this really is the electrode drop voltage drop, which is added as it is, and it is independent of the length of the arc column. So the voltage current relationship of an arc determines the required characteristics of the power source. In the figure on the right, we consider two different characteristics. For example, this is a linear characteristics, as you can see, this is a sharply drooping characteristics. So power, as you know, is VI. So therefore everything on this sharply drooping characteristics is basically the VI relationship that the power source would provide to strike the arc. So in this figure, two typical arc characteristics for two different arc lengths L plus delta L and L are also indicated. See the dashed line here. The intersection of the characteristic of the source and that of the arc determine the operating point. And I would like to just point out to a very important situation which is related to the stability of the system here. Let us look at the point D for example and the point B. So, these are actually points formulated where the intersection of the power source characteristic takes place with respect to the VI characteristics of the arc, and let us say we are moving from D to B. Okay. So, therefore, probably because the overall arc length is bulging and you are pumping in more voltage, you can see that the current is rising. Okay. So, if I consider the different abscissa and ordinate values here in this particular case, I can find out this to be I1 and I2, and I can find out this to be V2 and V1. So, obviously, you can see that corresponding to V1 there is a current I1, and if the voltage rises to V2, the current also rises to I2. Okay. So, therefore, the overall power would actually be V1 I1, and in the second case V2 I2, and you can see this power is more, the V2 I2 power is more in comparison to V1 I1. Okay. So, what you can understand out of it, that if there is an increase in the voltage, the power source which is having a constant power equal to Vi, okay, would ensure that the current reduces, so that it comes back to the normal point of operation D, whereas in this case it may not be the case. Supposing the characteristic is intersecting with a some power characteristics at C, let us say for example there is a point C here, and from C we are transferring to A. So, the voltage at C is Vc, current is Ic, and voltage at A is Va, current is Ia. So, as you can see here, with the reduction in the voltage, the current increases and still it is on the road map. Okay. It's all it's on the characteristic curve. Okay. So, therefore, this situation may easily be arised at, and the power source may be very happy to provide more current if the voltage falls down, and that way the voltage current characteristics keeps on unstably going away until it reaches this particular region. So, therefore, we call the points D and B to be more like a stable equilibrium, that whenever there is a increase in the voltage, it ensures, the power source ensures that the equilibrium point shifts back, whereas in case of A and C it may be considered to be an unstable equilibrium. So, please understand this concept very well, that A and C normally would not be self stabilizing, or if supposing there is a drooping down of the voltage, it will never come back to the point C, okay, because the Vi current is basically, the voltage current is going down, there is a downwards power, the power total overall power consumed for sustaining the arc is lesser and lesser. But in this case, as the power rises, obviously the arc will have to come back unless you wanted to of course blow off. So, if you need to prevent the arc from blowing off, obviously it has to come back to the point D from the point B. So, having said that, the other issue that I would like you to see here is that if you are considering both the flat as well as the drooping characteristics, as you can see probably here. So, this is a sharply drooping characteristics and this is a flat characteristic. These are two different power sources. I can easily find out what power source is suitable for what operation. For example, let us say when we talk about manual welding, manual arc welding, there is not a very high level of control, okay, which is there on the gap, the inter-electrode gap, because the electrode is going to be moved over the workpiece up to a certain extent, and because of that, in manual arc welding, it is always not sure what is going to be the operating length for the arc between the workpiece and the electrode. Okay. But if you look at the characteristics here, supposing there is a change in the arc length from L to L plus delta L, already the characteristics has gone up. If it is again increased to, let us say, L plus twice delta L, there may be a possibility that the power source characteristics may actually not at all have an operating point on this flat curve right here. Okay. So, if there is no control on the length particular by the operator, I think a drooping characteristics would be more feasible here, because of the sudden drooping nature or sudden change in the current because of the change in the voltage. There is still a scope of an intersection for a greater amount of length change in comparison to that of a straight line. Okay. So, for a straight line power, you can see that the it cannot really accommodate any more increase in the length from L plus delta L to, let us say, L plus 2 delta L, but the sharply drooping characteristics would still be able to draw some operating point, I mean, if you keep on increasing this VI relationship of the arc. So, what is it important then? So, then sharply drooping characteristics is normally the way to go when we talk about manual welding process, and we can say that with a flat characteristics for a big change in the arc length, there may not be any point of intersection between the arc and the source, and the arc may be simply blown out, and it may not be a very good feeding characteristics for a manual arc welding process. But for an efficient striking of the arc, it may also be necessary that the open circuit voltage, which is the highest voltage probably here, okay, where the current is more or less 0, the source should be high above the operating voltage of the arc. Okay. So, the more this voltage is, the better it is. Now, when we talk about when the flat characteristics could serve a better purpose, obviously the drooping characteristics would have a very quick response, in terms of VI variation, because of the nature of this curve, as you can see here, it is suddenly drooping down because of a large change in voltage corresponding to a small change in current. So, the question of flat characteristics come into picture when we talk about semi-automatic arc welding process, where the arc is maintained between the workpiece and the wire, which is driven forward at a constant speed. Okay. So, the idea is, in a semi-automatic process, there is a wire feed mechanism which sends out the wire, and then there is a workpiece which is there, and the arc is stuck between this wire and the workpiece, and this normally is fed forward. Okay. So, the wire is fed forward, and the idea is that the wire is made up of the filler material which melts away as it is fed forward, and as the welding happens lengthwise, in a lengthwise manner, let us say the welding is going in this direction. So, obviously, the melting is going to get deposited, okay, and so there is going to be a volume continuity for doing large welds of length L. So, an increase in the arc length in this case would increase the voltage, okay, as you can see probably here. So, the voltage has increased from let us say L to L plus delta L, and as a result the current should fall down. Okay. The melting rate becomes dependent on the current. We want to make the melting rate as uniform as possible. So, an increase in the arc length causes a decrease in the melting rate, okay. Because obviously the current would fall down because of an increase in the voltage. So, you can see that when the arc length changes from L plus delta L to, let us say, L some value, there is a rise in the voltage here and there is a fall in the current. Okay. So, if the reduction of the current due to an increase in the arc length is significant, the melting rate decreases considerably, so that the arc length returns to its original value. So, hence in this case a flat characteristics of power source would be more desirable. So, that is how you associate flat characteristics with respect to a drooping down characteristics. And having said that, now the important issue is what is the optimum power at which the arc should be operated, and what is the optimum length, for example, at which the optimum arc can do the power transfer. So, if I plot the arc power VI of the curve that I had shown earlier with respect to the various lengths of the arc, this is how it happens. The curve comes like an inverted curve like this, and then there is an optimum power at which you should always operate for, and there is an optimum length corresponding to this optimum power at which you should always operate for you to have maximum power used effectively and dissipated in a least manner. So, this procedure can be repeated for various values of arc lengths, and a plot of the arc power versus arc length can be obtained. Okay. So, optimum arc length, L optimum, can be easily determined. Since the electrode drop is utilized with a higher efficiency than the column drop, the actual optimum length is a bit shorter than the optimal length obtained in the figure, and for this kind of optimization, let us look at a numerical example how we would like to optimize the arc power. So, in this particular example, we have given a voltage length characteristics as 20 plus 40 L volts. L is the length of the arc in centimeters, is to be recorded. The power source characteristics is approximated by a straight line with an open circuit voltage 80 volts and a short circuit current of 1000 amperes. You have to determine the optimum arc length and corresponding arc power. So, let us first of all analytically write down the VI relationship. So, as has been recorded here that there are two statements, that is the open circuit voltage corresponds to about 80 volts and the short circuit current corresponds to about 1000 amperes. So, as the VI relationship is linear in this particular case, we can write V to be equal to A plus BI, where A and B are constants. This is like a straight line equation between V and I, the linear characteristics. So, having said that, if I wanted to apply the first boundary condition here, which corresponds to the open circuit voltage. So, obviously, I is 0 at open circuit, and so if we put I 0 value here, A becomes equal to V and V is 80 volts. So, therefore, A becomes 80 volts. Similarly, if I can solve this for the short circuit current. So, at the short circuit, basically the voltage is 0 because it is like a short circuited situation, it's a through current, through pass, no resistance. So, therefore, I becomes equal to minus A by B, okay, and A has already been found to be 80 volts earlier, and I, the short circuit current, is about 1000 amperes, meaning thereby that B becomes equal to minus 80 by 1000. Okay. So, that is how you can record B. So, V now can be written down as 80 minus 80 by 1000 I, and this is the linear voltage characteristics from the boundary condition that has been mentioned. We also know that V is written as 20 plus 40 L volts, where L is in centimeters. It has been given in the question itself. So, obviously, then 20 plus 40 L becomes equal to 80 minus 80 by 1000 I, and I can be found out in this particular case as 40 L with a minus sign plus 60 divided by 80 multiplied by 1000 amperes. Okay. So, that is how you can make I happen. So, you know that the power P is written as VI. So, in this case everything is determined in terms of L. So, already we have the voltage to be written as 20 plus 40 L, and the power and the current written as 60 minus 40 L times of 1000 by 80. So, that is how the power is determined. And in this case, if we apply the maximum power condition corresponding to the length L, the first derivative of P with respect to L should be equal to 0. So, we do that here. We have 40 times of, so 40 times of 60 minus 40 L 1000 by 80 minus of 20 plus 40 L times of minus 40 divided by 1000 or multiplied by 1000 by 80, it should be equal to 0. In other words, you can say 40 times of 60 minus 40 L equals 20 plus 40 L times of 40 with a minus sign, or that gives us a value of L equal to 0.5 centimeters. Okay. So, the optimum length then in this case L opt is found out to be 0.5 centimeters, and the corresponding arc power can now be determined. So, V becomes equal to 20 plus 40 times of 0.5 is about 40 volts. Similarly, the current I can be recorded as the relationship that you have between current and length here. So, I becomes equal to 40 times of 1000 by 80. So, this is about 500 amps and the total optimum power that comes into here is the V opt I opt, which is actually equal to 500 times of 40 volts, which is nothing but about 20 kVA. So, this is how the optimum power would be, and this is how the optimum length of the source would be. So, I would like to just illustrate here that whenever such design problems come through, you should be able to gauge by first converting the current into length terms and then multiplying with the voltage already present in length terms, so that you can have a power and then optimize the power with respect to the length to find out what is the operating point, and from the operating point you can always get the operating power, okay, at which you should actually operate, and this is the operating power which is drawn in order to ensure that hardly any dissipation happens and all the power is more or less a absorbed power, and there is hardly any reflected power from the system. So, that with that I think I would like to just sort of round off the arc design problem. There are many other sources of heat which are utilized from time to time for again doing the melting of the material in the welding process. So, in our discussion so far, we have mostly talked about DC arc, but there is also an existence of something called an AC arc, where there is an alternating current of 50 hertz frequency, and basically it takes about 0.01 seconds to reach the equilibrium state. So, this is a sort of a quick response system, okay, and although the equation is actually determined by the same manner, A plus BL is equally applicable, but it is true for every half cycle, because the polarity would change after every half cycle, and then the arc may as well need to get reignited for every half cycle. So, therefore, it is important for the designer to ensure that the coatings that are there on the electrodes are of materials which has a lower ionization potential. So, in this AC arc welding case, mostly the coating is potassium silicate binders. It makes sort of a very good stable AC arc, but if the coating is changed to DC arc, then something like sodium silicate also would result in a stable arc or striking an arc, because we do not need really a low ionization potential in this case. In AC arc, however, the reignition factor comes into picture. So, therefore, always the arc becomes stable if the ions which are present are easily ignitable, that are easily they can easily ionize, and they have a overall lower ionization potential. In fact, potassium silicate binders, when they evaporate, they do produce very easily ionizable constituents, which would be in the gaseous atmosphere, where there is this electron, the secondary electron which would get produced, okay, the free electron which would get produced because of the presence of such binders. There are many other sources, as I had discussed, like the chemical heat source, where you can use acetylene and oxygen to produce gas flame. So, acetylene and oxygen burns out in different conditions. So, in the presence of excess oxygen, for example, it burns according to this reaction right here, C2H2 plus 5 by 2 O2 is twice CO2 plus H2O plus heat delta H1. This is a highly exothermic process again. The amount of heat liberated delta H1 is about 1.275 times 10 to the power of 6 kilojoule per kg mole of acetylene. If the oxygen is premixed with acetylene, 1:1 mole ratio, then the combustion reaction becomes equal to C2H2 plus O2 is twice CO plus H2. So, you can see that it is starved of the oxygen. Here it was an abundance of the oxygen supply. So, in kind of premixed cases, the H2 that is generated here is comparatively lower in as in case of excess oxygen, and the carbon monoxide and hydrogen produced later burn out again at a second step or additional step to produce about 0.827 into 10 to the power of 6 kilojoule per kg of acetylene. So, this heat however is generated over a large volume and at a low temperature does not add much to the welding process. Once the amount of heat liberated delta H is known, we can roughly estimate the maximum flame temperature with the assumption of an adiabatic flame. With an assumption of an adiabatic flame, which means really that the entire enthalpy change which happens is because of whatever heat transfer takes place out of the flame through only the heating of the reaction products, okay, and nothing else actually. So, care must be taken to subtract the latent heat if supposing there is a phase change associated with some property or some of the gas maybe and therefore, maybe there is some water vapor or something which is present, and then there is some kind of an absorption from this particular enthalpy change in terms of heat of latent heat. So, that has to be taken out of this delta H. So, supposing delta H is the total amount of heat which is transferred adiabatically through the flame because of the heating of the reaction products, and latent heat is let us say taken off from delta L. So, that is actually the total amount of enthalpy change produced, and it can be put together as a integral of n Cp theta d theta, theta varying between theta r to theta t. Theta r is the room temperature, and you can assume that the summation is taken over n moles of each of the m reaction products which are present, and theta p or Cp theta is basically the molar specific heat capacity of these products which vary with the temperature. Okay. So, from this you can really calculate the room temperature theta t once the so the flame temperature theta t once the room temperature etc., and other values like Cp theta etc. are plugged in into this equation, and delta H dash is basically the total amount of heat generated by the reaction products. So, typically for the acetylene reaction mentioned earlier, the flame temperatures which are obtained are around 35-60 degrees Celsius, which is good enough for melting of metals, particularly iron based metals, whereas the measured temperature of the flame varies between 1280 degrees minimum at the tip of the flame to 3250 degrees maximum at the core of the flame. So, another chemical source which are normally used are for in this case is probably the thermites, which are any transition metal oxides like iron oxide, copper oxide, bismuth oxide, so on and so forth, and aluminum, and these are also again very effective in generating heat to an extent where the adiabatic temperature is calculated to be about close to 3000 degrees Celsius in such sources. So, therefore, we studied about oxyacetylene sources, we also studied about this thermite reaction based sources. So, now we will try to look at another aspect of the heat source, which is basically the contact resistance heat source, which happens in most of the industrial applications related to automotives etc., where spot welding is a very important phenomena. So, as we know that the electrical resistance heating is also responsible for doing joining, and it can also be used as a local heat source, an intensely high temperature heat source, and this may be done either by utilizing contact resistance of the interfaces, okay, as in various resistance welding processes, or by utilizing the resistance of a molten flux and slag as in the electro slag welding process. So, both are contact resistance based heating, and we have already noted in the earlier section that when two metallic surfaces are brought into contact, a small fraction of the apparent area is the actual metal to metal contact. So, supposing there are these tiny metallic bridges which would happen between two such materials, you can see these bridges getting formulated here because of whatever deformation etc. And so, if I assume the radius of such a bridge to be r1, so this is r1, small r1, and we also assume that between the two bridges is a gap of about 2r2. Okay. So, we can easily calculate the contact resistance, and this comes from the electrical engineering theory of contact resistances between surfaces, which I am not going to go into, but for such spherical constructions, let us say there are n such constrictions per centimeter square, you have a resistance, a half resistance done by this half bridge which actually connects between both the potential points across the two different members, is given by rho r2 minus r1 by s, where s is actually the geometric mean between the two times the circular area pi r2 square and pi r1 square. So, I do not want to really get into the proof of this, because this is actually available from contact theory, okay, or contact resistance theory, but just in the interest of time I would go ahead and apply these in order to calculate some of the resistances and some of the heating effects which would lead to a temperature rise in this situation. So, the resistance between now these two plates with n parallel bridges across each other would be actually each bridge would have a resistance of rho r2 minus r1 by root over twice pi r2 square times of twice pi r1 square, which actually becomes rho times r2 minus r1 divided by 2 pi taken common r1 r2. And if I assume that R2, the resistance between the bridges or the area between the bridges is much larger in comparison to R1, then this resistance between of each bridge comes out to be equal to rho r rho divided by twice pi R1, and we can assume that half bridge contributes this. So, therefore, both the half bridges here and here are in series. So, the total resistance should be twice rho by twice pi r1, and there are n such bridges per unit area in centimeter square. So, these are all, then these n bridges are more or less parallel resistances. You can assume that